The newly laid asphalt, dark and uniform, looked perfect. Until time starts to take its toll. First, almost invisible cracks, then ripples, potholes, patches, trucks passing by, intense heat, constant rain. And gradually that smooth surface turned into a mosaic of wear and tear. Then the machines would come again, and everything would start over. Again. Build, watch it degrade, intervene, fix, and start again. A continuous, costly cycle, increasingly pressured by heavy traffic and harsher weather conditions. However, this scenario may be changing. A new approach is starting to gain ground in Brazil, promising to increase the durability of highways, reduce maintenance costs, and speed up the execution of construction projects. At first glance, it seems like just an evolution, but it's not. It's actually a different system. A dry, compact concrete mix applied with similar equipment, but offering much superior structural performance. Stay with us for the next few minutes and understand why RCC technology can transform the future of roads in Brazil. Although today it appears as an innovation, roller compacted concrete, or RCC, has an origin that goes back more than half a century. In the 1970s, engineers were looking for solutions to speed up the construction of large dams, reducing costs without compromising structural strength. It was in this context that a different concept of concrete emerged, drier and denser, capable of being compacted by heavy equipment, as if it were soil. Over time, this technology began to migrate to applications where wear is extreme. Ports, logistics terminals, industrial yards, and airports started using RCC precisely because of its ability to withstand repeated loads without deforming. These environments function as a real testing ground, where the material was subjected to much harsher conditions than those found on conventional highways. Even with consistent results, high durability, low maintenance, and excellent structural performance, its use on roads took a while to become established. There were no specific standards, standardized construction procedures, and above all, adaptation to Brazilian conditions. However, this scenario has changed recently. In 2025, the National Department of Transport Infrastructure, ZNIT, updated the technical standards for the use of RCC in rigid pavements, paving the way for large-scale application. By 2026, what we see is a clearer movement from the experimental field to broader applications. But this raises an important question. If the material has existed for decades and has shown superior performance, why is it only now preparing to gain ground on the roads? The answer lies precisely in the way it is constructed. And that's where the logistics of the engineering process change completely. To understand the impact of RCC, you need to start with the basics, not with what this technology has in common with traditional concrete, but with what makes it completely different. Although it uses the same components, cement, aggregates, and water, the behavior of RCC is radically different. The amount of water is so low that the mixture is practically not fluid at all. In practice, it doesn't flow, it's almost dry. Instead of a plastic moldable material, what you get is a mass with a granular appearance, similar to moist soil or slightly damp gravel. This characteristic completely changes the construction method. There is no placement into forms, no internal vibration, and no conventional finishing. The process is much closer to an earth-moving operation than to traditional concreting. Everything starts at the plant. In the production of RCC, there is strict control over the size and distribution of the particles in the aggregates, or in technical terms, their gradation. This is essential because the smaller the volume of voids, the less cement paste will be needed to fill them, which directly impacts the cost and performance. After being produced, the material is transported to the construction site and spread by pavers, similar to those used for asphalt. By the way, this is a key point. RCC uses an existing paving infrastructure that is already well established in Brazil. The real difference appears in the next stage. As soon as the material is spread, the compacting rollers come into action. Heavy machines, often vibratory, that repeatedly go over the surface until the specified density is reached. It's at this moment that the material gains structural strength. Unlike conventional concrete, where strength is strongly linked to the hydration of cement over time, in RCC, compaction is a decisive factor from the very beginning. This process creates an extremely stable structure with few internal voids. The material has high stiffness and load distribution capacity. Instead of concentrating stresses on the surface, as happens with asphalt, RCC distributes these loads over a larger area, reducing internal stresses and preventing permanent deformations. Another important point is the construction speed. Since there is no need for forms, reinforcement, or complex finishing processes, the construction progresses continuously. Under certain conditions, it is possible to achieve high daily productivity, allowing earlier reopening to traffic than with conventional rigid pavements. In addition, RCC has excellent thermal behavior, unlike asphalt, which can soften under high temperatures. Concrete maintains structural rigidity. Thus, rutting is reduced, one of the main problems on Brazilian highways with heavy traffic. In recent years, the technology has evolved even further with the incorporation of fibers. These fibers, which can be polymeric, metallic, or aramid, act as micro-reinforcements distributed throughout the concrete matrix. They increase toughness, control crack propagation, and improve fatigue performance. This reinforcement is especially important in pavements subjected to repetitive loads, such as logistics corridors and high-traffic urban roads. Another recent advancement is in surface finishes. Traditionally, RCC has a rougher texture, limiting its use on higher-speed roads. Today, techniques such as surface milling and diamond grinding make it possible to achieve comfort and grip levels compatible with modern highways. In addition, planning the joints, whether natural or induced, is essential to ensure proper performance over time. Without this control, unwanted cracks may appear. That's why RCC requires not only technology but also construction discipline. When well executed, however, the result is a robust pavement with high structural capacity, less need for maintenance, and consistent performance over decades. To understand the real impact of RCC, you need to move beyond theory and translate engineering into numbers. And, most importantly, in everyday situations, starting with durability. While a conventional asphalt pavement usually requires significant interventions, between 8 and 12 years, roller compacted concrete can last over 20 years in certain applications with low maintenance requirements, depending on the project conditions and application. In practice, this means that, in the same period, an asphalt road may undergo 2 major rehabilitations, while RCC can maintain more stable performance over time. Now imagine this as a staircase. On a 100-kilometer stretch of highway, the traditional model may require 2 major projects over 20 years, but with the CCR, that same stretch can go through the entire period with significantly smaller interventions. It's like reinforcing a house twice while another one remains practically untouched. Another critical point is deformation. RCC significantly reduces this problem because it's a rigid pavement. It maintains its geometry even under repeated loads. This results in fewer irregularities, greater driving comfort, and most importantly, a significant reduction in maintenance costs over time. Now, looking at the construction process, conventional concrete, although durable, requires forms, reinforcement, and a longer curing time. On the other hand, RCC uses equipment similar to that used for asphalt and allows construction to move forward continuously. And for those who use this road, this makes a direct difference. Less roadwork, less traffic at a standstill, less maintenance, fewer detours, more durability, more predictability. Internationally, these benefits have already justified its adoption in different applications. In the United States, RCC is used on urban roads, industrial areas, and secondary highways, especially in regions with constant heavy traffic. In several countries, it is associated with the expansion of logistics and industrial infrastructure. In Brazil, an important example is in the metropolitan region of Fortaleza, in Ceará, with the use of RCC on the 4th Ring Road. This is a strategic road aimed at cargo flow and the redistribution of urban traffic, where the choice of material was guided by technical and operational criteria. However, there is a fundamental point. This project was not carried out under the current DINIT 460 standard of 2025. It predates the most recent standardization, having been resolved based on the previous guidelines. This makes the case even more relevant because it shows that the RCC was already being applied in Brazil even before the current regulatory consolidation, functioning as a full-scale laboratory. In the end, more than just a technical alternative, the RCC represents a change in logistics, moving from a model based on constant maintenance to one based on durability. In fact, the consolidation of the RCC in Brazil is still underway, but the foundations for its expansion are already in place. The existence of a national technical standard creates a safer environment for investments, reducing risks and allowing projects to be structured with greater predictability. From an economic standpoint, the impacts are direct. Less need for maintenance means reduced costs throughout the highway's life cycle. This not only reduces public and private spending, but also decreases traffic interruptions, which is a critical factor for the logistics of a country with continental dimensions. In addition, the faster execution speed helps to deliver the infrastructure sooner, speeding up the return on investment and improving the operational efficiency of the roads. Another key aspect is the environment. RCC reduces dependence on petroleum derivatives and over time can absorb some of the CO2 present in the atmosphere through carbonation. In a scenario where infrastructure, efficiency, and sustainability go hand in hand, RCC emerges as a solution capable of aligning technical performance with economic and environmental responsibility. Roller compacted concrete is not a recent innovation. It is the result of decades of technical evolution, testing in extreme environments, and progressive adaptations. What changes now is the context. With standards, technology, and demand aligned, RCC is no longer a niche alternative and is starting to take its place in road infrastructure. More than just replacing existing methods, it expands the possibilities of engineering, showing that innovation is often a matter of application. Thank you for watching this video until the end. What do you think about this great technology? It should have been applied in Brazil a long time ago, right? But where? I'd like to hear from you. Where would RCC need to be applied right now? Leave your opinion in the comments. I'll be happy to read them all. That's it from me for now. Take care and see you in the next video.